Well, let's start. Now, today we will discuss about potential functions. Well, we have discussed about potential, about electric scalar potential, about magnetic scalar and magnetic vector potentials in previous sections, and today we revisit the idea of scalar and vector potentials, but now the potentials are time dependent. Well, we discussed the potential functions in terms of time dependent as time dependent functions. Okay, so time dependent potential functions. So before we start discussion, let's recall some properties of vector fields or vector functions. So if we are given some vector field f and a rotor of this vector field is 0, this vector field is called rotor free. Rotor free, and this for this vector field, for the vector field f, we can find a scalar function which describes fully our vector field, or okay, namely, so or we can describe f as a gradient of some scalar function. Here omega is scalar function. Okay, and another types of vector fields. So if the divergence of our vector field is 0, is called this type of vector field called a divergence free. So okay, divergence free, and in this case we can write our vector field as a rotor of another vector field W, where W is a potential vector potential. So well, however, in general, we may use both scalar potential and vector potential, and so in case where, so if some generic vector field G, if we are given some generic vector field G which is neither rotor free nor divergence free. This vector field can be described as gradient of some scalar function u plus rotor of some vector function c. Here here u can be thought as u can be thought as scalar potential, and c can be thought as vector potentials, as we did in previous slide. In this slide, the W is vector potential. Vector potential. Okay. So, okay. Well, thus the general process of defining scalar and vector potential for vector fields is as follows. If a vector field is curl free, which is curl free or rotor free, it doesn't matter. So first, if I define by f some generic vector field. If f is curl free or rotor free, a scalar potential may be defined which completely describes a vector field. So we may define, if f is curl free, we may define some scalar potential, for example omega, which can describes f completely. We have seen the demonstration of this in this slide. If f is rotor free or curl free, doesn't matter. We have one scalar potential omega. Okay, omega is also a generic scalar potential which can describe our vector field f completely. Second, if our vector field f is divergence free, now we can define a vector potential. Vector potential in previous slides we defined as W. Vector potential, which describes our vector field completely. Okay, it describes f completely. Okay, if if our vector neither divergence free nor rotor free, uh, okay, for general vector field F, we are required to define both a potential, a scalar potential, and vector potential. So both scalar and vector potentials are sorry, are required to uh, define or to describe our vector field completely. This also we have seen in, okay, here we have seen we define a scalar potential U and vector potential C, and these two quantities describe our vector field G completely. Okay, now, so so now let's see let's see very quickly scalar potentials and magnetic vector potential. So we have already discussed the electric scalar potential, and also we haven't discussed, but there exists also magnetic scalar potential. And okay, well, also regarding to the Maxwell's equations, two scalar two two scalar potentials can be defined, which are electric scalar potential and magnetic scalar potential. And if uh, if time derivative of magnetic flux density in Faraday law is zero, in this case, electric field intensity is curl free. It means uh, so electric field intensity is curl free, means the rotor or curl of electric field intensity is zero, and from this comes that we may define for our electric field intensity a scalar potential V, which completely describes the electric field intensity. And for mag for magnetic fields, if the magnetic field intensity is curl free, or in other words, the rotor of magnetic field intensity is zero, so magnetic field intensity can also be written as a gradient of scalar function psi, where psi is magnetic scalar potential. Okay, this is magnetic scalar potential. Okay. Now, the electric scalar potential V and the magnetic scalar potential psi can only be used by themselves for static electric and magnetic fields. Can only be used by themselves in static electric or static magnetic fields, because only under static conditions can because only under static conditions electric field intensity can be curl free and magnetic field intensity also can be curl free. Uh, but they are also useful in general electromagnetic fields in combination with vector potentials. Now let's switch to magnetic vector potential. Okay. Magnetic vector potential. So we know that magnetic flux density B is equal to the curl of magnetic vector potential. Yep, because the divergence of magnetic flux density is 0. So it means that because of this, because our magnetic flux density is divergence free, we can define a magnetic vector potential A, which describes the magnetic flux density B. Well, this also applies to time-dependent magnetic fields because the definition is based entirely on the divergence-free condition of the magnetic flux density. Well, magnetic vector potential may be used in many ways. So magnetic vector potential A may be used in many ways. Uh, here, here we will use the function to represent Maxwell's equations, and in the process to show that it may be used for calculation of field quantities. Field quantities that are maybe magnetic flux density B, electric field intensity E, or others. So let's use Maxwell's equations. First, Maxwell's equation. Okay, let me scale down. Okay. Well, what was the first Maxwell's equation? So where are the Maxwell's equations? Okay, first Maxwell's equation is this 11.5, which says the rotor of electric field intensity E is equal to the minus dB over dt. So let's write the okay rotor of electric field intensity E equal to the minus dB over dt. Yep. Now let's put this expression into B. What we have? We have rotor of electric field intensity E will be equal to minus d dt of curl of A, and if we manipulate the so I don't need lagoon, and let's if we manipulate a little bit the rotor of electric field intensity E will be equal to the minus not minus okay rotor of minus dA over dt. Here I just changed the divergence with derivative. I just changed the places of divergence and derivative. Now, what we have? If we move everything on the left hand side, we have curl of electric field intensity E plus curl of dA dt is equal to sorry, here should be cross product of dA dt will be 0 will be 0. Okay, now if we manipulate again curl of electric field plus dA over dt equals 0. Now what we have? We have a vector field which is curl free. It means okay, curl free. Curl free, which means the rotor of this vector field is 0. Now, from the definition that we gave before, we may conclude that if our vector field is curl free, we may define for this vector field one scalar potential, and we may write our vector field which is curl free dA over dt as a divergence of scalar potential, in our case V. So now electric field intensity E. Oh, this is awful. Okay, electric field intensity E become minus divergence of V minus the derivative of vector potential of magnetic field. This is the more general expression for the electric field intensity E in time dependent fields. So this form, okay, this form is a general electric field intensity. So of course unit of measurement is volt per meter. This form is exactly that which was required by our equation. Okay, here we defined. Okay, if we are given a generic vector field, we need scalar potential and vector potential in order to describe fully our vector field. Now here we have a scalar potential and a vector potential which is describing our vector field completely, Okay, now let's move so let's move to the second equation of Maxwell equations. Second equation was, so here second Maxwell equation says that curl of magnetic field intensity H equal to here J plus d the d over the t. Okay. And what is H? This is magnetic field intensity and is equal to mu multiplied by B. Yep. Okay, what is J? We know J. What is this expression? We also know this expression is the displacement current density. Now, sorry. Uh, sorry, I made a mistake because that B equal to mu H, so H will be equal to 1 over mu by B. Sorry for that, I did mistake before. Okay, and in turn B is equal to rotor of A. Yes, rotor of A. And what is D? D is epsilon multiplied by electric field intensity E. And electric field intensity was defined now by ourselves is equal to minus gradient of V minus dA dt. So minus gradient of V minus dA dt. So if we rearrange our equation, if we rearrange this equation with all these quantities, this equation becomes rotor rotor of 1 over mu of rotor of A will be equal to J plus okay, the time derivative remains multiplied by epsilon by minus dA over dt minus gradient of V. So, okay. Okay. Now, okay. So, let's rearrange one more. For example, we multiply by mu both sides of equation, and what we get, the rotor of rotor A will be equal to sorry, this is awful. It was 2.1 or 2.3. 2.1 is okay. So we have rotor of A is equal to mu J minus mu epsilon d squared A over dt squared minus mu epsilon of gradient of V. Sorry, mu epsilon, and here we also have a time derivative of gradient of V. Okay. What's next? The next is again rearranging the terms. For example, rotor of A was equal to So gradient of divergence of A minus the Laplacian of A. And now let's okay, and what is next? Next, we just put this here and we get the gradient of divergence of A minus the Laplacian of A equals to again, well, mu j minus mu epsilon d squared A over dt squared minus this term. Here also we change the operator nabla and operator del and the time derivative, and we get gradient of mu epsilon of dv over the t. Okay, now the how we can proceed further. We just we can just imagine that uh, corresponding terms of the left hand side and the right hand side are equal. I mean, the Laplacian of A involves double derivative by time, or just simply here Laplacian of vector field A involves double derivative, and on the right hand side we have for double derivative this term, and we assume that these terms, we expect that these terms to be equal, d squared A over dt squared. Oh, let's continue. And okay, here one more thing that I have done a bit confusion. So okay, first we need to take the divergences. So, and what we get is divergence of A is equal to minus mu epsilon of the V over the T. So this is the first. And The next relationship becomes what? Becomes minus the Laplacian of magnetic vector magnetic vector potential is mu j minus the and minus of course mu epsilon d squared a over d t squared. Now it's correct. Before I did a mistake. Okay. So now this equation is equivalent equation from the Maxwell's equations. That is instead of solving Maxwell's equations for the magnetic field intensity and electric field intensity, we can solve for magnetic vector potential A. We can solve for magnetic vector potential A and then obtain the magnetic and electric field intensities. In intensities, it means that if we solve the equation for magnetic vector potential A, after we can define electric scalar potential, and if we know electric scalar potential, we can define electric field intensity and again, if we know magnetic vector potential A, we can simply find magnetic flux density B or magnetic field intensity H. Okay. So okay, now you may have a rest a little bit, maybe 5 minutes, and after that we continue with some examples. Okay, please have a rest.